neural networks. We're going to do a cross comparison of the Boltzmann machine, specifically the restricted Boltzmann machine, and CORTECONs. We're going to use the idea of a neural network sandwich to illustrate our points here, and it's going to be a very simple sandwich: an input layer, an output layer, and of course the middle or hidden node or latent layer. We're going to use this to illustrate both the Boltzmann machine and CORTECONs. We're beginning with the makings for a cheese sandwich. What we have are mayonnaise and mustard. And we're going to make this little story up in our minds. The mayo, white, is cool. Get it into certain spots here, because the idea is we don't want an even smear. These are our connection weights. So you're going to have cooler connection weights in one spot, warmer connection weights in another. We add the mustard, again in globs, because these are connection weights. Ooh, I just spilled a lot of... So I'm putting this into spots where I don't have the cool white mayonnaise connection weights. I know, I'm just totally making this up. I mean, don't take me seriously, okay? Not that you do, but just in case you were going in that direction. So, you can hear the blurry sound effects as I'm doing this thing. Now, mustard and mayo, connection weights, two sides of this neural network that when sandwiched together give us input and output layers. Now here's where things get interesting. We're going to have two different kinds of cheese. Did I mention that this was a cheesy video? I know. Bad pun. I've got cheddar and pepper jack, just what I had in the fridge. This sort of came out, sort of randomly. And I'm going to start putting the latent variable node in on the input layer, the bottom layer of the sandwich. And I'm going to make an important point really, really soon as I get some of this pepper jack on there. There's a reason, besides trying to talk about nodes, that I've got these as separate little bits of cheese. And the reason is this. In neural networks, the whole point in a neural network with latent variables, when you're building a Boltzmann machine, just assume that I'm talking about restricted Boltzmann machines, so there's no crosstalk between the latent nodes, and the same architecture would apply to a multi-layer perceptron. So this discussion sort of pertains to both. So here's the important notion. The important thing with latent variables in these simple classifier type architectures is that you want to minimize the number of latent variables. That's why I'm not putting on big slabs of cheese. Instead, we have distinct nodes and they are separate from each other. And now I'm going to assemble the sandwich. And in a moment I'll take it off to the kitchen and fry it up. And then we will have melted cheese. And the nodes are going to smear out a bit because each node generalizes during training. So we're frying it up in the frying pan with a little butter on each side. That's training our neural network, okay? The node spreads out. It generalizes. It encompasses a little bit more. Really a loose analogy, but I think you can, go along with me just for the sake of humoring me if nothing else. So this is the Boltzmann machine architecture. Relatively speaking, we've got a minimalist number of nodes, just enough nodes to be covering the space, the latent space, where we have our features. So we don't want too many, because then we have those typical old problems of nodes that were training to recognize the same thing, or nodes that weren't training for anything at all, just totally lazy, they never got trained, or nodes that hyper-specialized on one input pattern and they were great at recalling that pattern in its completeness, but they weren't generalized at all. They were like single pattern recognition units. So those things creep in if we don't force our nodes to generalize. And the way that we do that is we have just the right number of nodes. Kind of the mama bear in the Goldilocks story. Not too many, not too papa bear, not too few, not baby bear, mama bear. Middling a number of nodes, just what we need. Okay, we've got this. I'll fry this up in a moment, but we're going to shift gears and talk about CORTECONs. Indulge me, please, and let me elaborate just a little bit more on this point before we move on to CORTECONs. I was looking recently at an experiment done by somebody who was playing with a multi-layer perceptron just to get a sense of how the various latent nodes responded as these various nodes developed their feature recognition capabilities. So this person experimented with a very simple classification. There were just 3 output nodes, a set of input nodes that represented pixels in a simple grid that allowed alphabet representation, and for this experiment the person selected 6 nodes in the middle or latent layer. And not surprisingly at all, in fact, this is a completely predictable result, one of those nodes lit up strong and hard for all 3 classes. In essence, that node's activation was wasted because it was responding equally to each of the input activations. Several of the other hidden nodes didn't train at all, so they were also wasted. And then it turns out that out of those 6 hidden nodes, 1 each got active for each of those specific 3 training patterns. Now, this was a hugely simplistic example, so we're not expecting a lot, but it illustrates that you need to force the nodes to generalize, and one way in which to do it is to have a minimalist number of nodes, which has been the backbone of basic neural networks for the longest time, going all the way back to Gorman and Sejnowski back in 1988. I talked about this a good deal more in a previous YouTube. That one's called The Matrix. So if you would, please check it out. I'll link to that in the blog post that will be associated with this. Round 2. We're going to switch from a cheese sandwich to a tuna, or Hawaiian term, ahi, and salmon sandwich, simply because I was at Costco very recently and was able to pick up an ahi salmon sushi platter. So what we have is a CORTECON. A CORTECON is a neural network sandwich with, instead of having the sparsest number of hidden nodes possible, we have as fat a number as we can possibly manage in there. I'd say minimally, just for toy purposes, I'm working with 16 by 16 grids. They're in a very specific grid layout. They touch each other. You can count up not only how many nodes you have in each state. Here I've got 10 ahi nodes and 10 salmon nodes, but you can count nearest neighbors. So I'm going to start with a piece of salmon in the center, and to its upper left diagonal, that's one of its nearest neighbors. We've got another piece of salmon. To its upper right, we've got a piece of ahi. Lower left is another piece of salmon. Lower right, these are all diagonal, is an ahi. Going left and right is actually the next nearest neighbors. You have to have sort of wide nodes to make this work, but it works. So to the left, ahi. To the right, salmon. 2 rows up is ahi. 2 rows down is ahi. To that lower left corner, we've got a cluster of these pink salmon nodes. To the lower right, we've got this cluster of darkish ahi nodes. Now, clusters are useful. The reason that we want clusters is that you don't have to rely on just getting 1 node active per feature. We'll start our training in the usual manner, okay? Then we're going to freeze certain nodes in the on state, and those will be the ones that tend to be more or less central to a cluster, and then we keep doing the free energy minimization until we get clusters forming where a group of nodes are all on, and presumably over various training rounds they will become on for the same feature. So you could have, in this case, lower left, I've got 5 salmon nodes, and they are all off together. In our little notational scheme, we're attempting to match things up with the black and white PowerPoints that I produced earlier. So the darker colored ahi nodes are the on nodes, and the bright orange salmon nodes are off. So in the lower left corner here, we have a collection of off salmon nodes. Now, I could stop the input stimulus to this, and what that would do would be an opportunity to interchange the salmon with an ahi. We're making a notational statement. Okay, so we've got this scenario where the pale pink salmon is off and the dark ahi is on, off and on nodes. And I'm going to get a picture with where I've just interchanged one of the pale pink salmon nodes with an ahi. In this little example, I've done something that we're not typically going to do, at least for a while, in our studies, and that is that I've increased the number of on nodes. We've gone from 10 on ahi nodes, the dark rows, to 11. And of course, we dropped the number of salmon nodes down to 9. What this means is that we now have more nodes in the active state. Now, the only way to do this, yes, to some extent this can be done by putting in an input stimulus, but to keep the total ratio of on nodes stable at a certain level, we need to play with our epsilon 0 parameter, which is the parameter that governs how many nodes, the fraction of total nodes, that are in the on state. Now, even though I've just touched on what can happen when we play with the epsilon 0 parameter, that's the activation enthalpy, we're not going to go there today, and the reason is that we want to keep epsilon 0 at 0, meaning that we'll keep an equal number of on and off nodes. And the reason for that is that it lets us line up the various configuration variables, those are the nearest neighbors, next nearest neighbors, and triplets, with what we would expect with an analytic solution. That analytic solution is good only when we've got equal numbers of on and off nodes. So instead, we're going to put our attention on what happens when we swap out some of those existing nodes. We've got one of those ahi pieces that is on and it's in the middle of a salmon cluster. I'm going to change that and replace that ahi with salmon. And what that gives me is a big fat salmon cluster. Because I want to keep in touch with an analytic solution that works only when you've got equal numbers of on and off nodes, I'm going to replace one of the pink salmons with an ahi. So I'm going to pick this one up here. We just upped the clustering. Now the way that we would do this, and specifically using the cluster variation method, I'm going to call it CVM, cluster variation method, for this middle layer, is that we've got two parameters. Epsilon 0 controls the on-offness of nodes. We're going to keep our epsilon 0 at 0, meaning we're going to always maintain an equal number of on and off, and that lets us reference an analytic solution, which is really important right now because we're just getting started. Now let's play with our epsilon 1. That's the parameter that controls clustering. If I increase my epsilon 1 parameter, and what that's also going to do is increase my H value, and the analytics just work more nicely when I've got an H value instead of epsilon 1. When I do that, when I increase that, I increase clustering. So we're going to go from random assignments of nearest neighbors and next nearest neighbors to more of a definitive clustering. Just by swapping out two nodes, I swapped the places of one salmon and one ahi, I greatly increased the clustering in this very small sample. And that's the important thing with the CVM. So here's the important thing. When we interchange two nodes that have different activations, as I just did, I just swapped one salmon and one ahi, and I got clusters, whereas previously things were sort of distributed amongst the different kinds of nearest neighbors and next nearest neighbors. But now we're much more clustered. And what that did, this is so important, it changes the entropy of the system. With the CVM, the entropy isn't just a function of the total number of on and total number of off. We've been controlling that all along. We've got a system, so to speak, with 10 on nodes and 10 off nodes. We haven't changed that. We've been playing with what we call the configuration variables, the nearest neighbors, the next nearest neighbors, the triplets, and all of a sudden we've gone from a semi-quasi-random distribution to very definitive clusters. We've dramatically shifted the entropy. No other system in neural networks lets you do that. In a Boltzmann machine, you fix the entropy when you set up your data. And the notion of interchanging positions is really not relevant because the positions of these nodes in a Boltzmann machine doesn't make any difference. Here, the fact that we've got a physical configuration makes sense in a latent space. They don't correspond to anything in the physical dimension. This is not a CNN. These are not corresponding to features in a visual field. No, what we're actually generating are clusters of nodes in the latent space. And as we form clusters and then open up those clusters, creating smaller clusters, which we can do when we stop giving input activation to the system, we can slowly dissipate the edges of the clusters, and then out in that sea of things that are sort of on and off but not particularly cluster defined, we can change that composition a little bit. We can ease off on the cluster but still keep a trace activation going on for a previously presented pattern. Once you have a pattern presented and it maintains its activation over a period of time, perhaps diminishing, perhaps some of the nodes in the cluster are turning off. You can still maintain communication between nodes, and I'm going to do that. Little tiny bit, little tiny cucumber slice. I'm going to take an ahi on the far right and connect it to an ahi in the cluster on the upper left. Take a quick picture of that. Don't laugh too hard, okay? It's what I had in the fridge. I'm just playing with my food, don't take me seriously. I can make a connection between those two ahi pieces. If this reached further, I could get further up into that ahi cluster. I think we should all be glad that this is as far as the analogy goes, because it's getting to be too silly. So let's sum this up. There's actually some meaningfulness to this. First of all, we've got a new neural network. It's actually a new class of neural networks. We train activations the way that we typically do to get started. Backpropagation, Boltzmann machine training, doesn't really make a whole lot of difference. Just get that first pass of nodes trained. Then you start forcing a little coagulation by varying the epsilon1 parameter. Get some clustering going. That way you can start to get a number of nodes that respond to the same feature on at the same time. Turn that feature off. And here's the big thing that doesn't happen with the other neural networks. You can get a slow activation decay going on where you insist that to some degree you maintain a free energy equilibrium state. And you do that by allowing your interaction enthalpy parameter to decrease so that you don't force as tight a clustering. So the clusters start to break up and you get little random odd bits, and maybe some previous clusters that had degraded earlier but still have a lingering little bit of activation going on. They could wind up even picking up a little activation on their sides. As you get this going, you can not only get remnants of prior activations to be active, you have the option for the first time in decades to start playing with mechanisms for having communication across that latent layer. Now this is something that's used in the brain a lot. We've just simply, over the past 3 decades really, we've simplified and simplified and simplified. We're going, right now in our architectures, we want as few nodes as possible, and we want them as simple as possible. We use ReLUs in the CNN, for example. Nice, very effective for getting a CNN to work, but not necessarily what we want if we're going to build more comprehensive and interesting architectures that lead to AGI. Thank you so much for being with me in this very silly little vid. It's getting close to the end of the week and we're just playing. And guess what? We've had a discussion on how CORTECONs work with not a single equation in sight. And that is something to be enjoyed with perhaps a good ahi sandwich and a glass of Chardonnay. Have a lovely time, my dears. We'll see you soon. This is Aliane Moran signing off from Nemesis.